In the last video, we talked about how to derive the sum and difference formulas for sine and cosine. And in this video, we're actually going to talk about how to use them. So something I want you to note. Sometimes we write that the sine of alpha plus or minus beta is equal to the sine of alpha times the cosine of beta plus or minus the sine of beta times the cosine of alpha. And then sometimes we also write that the cosine of alpha plus or minus beta is equal to the cosine of alpha times the cosine of beta minus plus the sine of alpha times the sine of beta. So this symbol may be new to you. It simply means that that symbol is the opposite of whatever symbol was here. You also tend to remember, or at least I do, that our cosines stay together for cosine, but our sines seem to split everything up. So those are just some little ways that I remember it. All right, on to the problems. So the first example I want to go over is using the sum and difference equations to find the exact value of the sine of 15 degrees. So the first thing I want to think about is, okay, I need to find some things that have a sum or a difference of 15 degrees. So there's a couple of ways that you can think about this. We can actually say 60 degrees minus 45 degrees is going to equal 15 degrees. We can do the same thing with 45 degrees and 30 degrees. Their difference is 15 degrees. You can use either of those. I'm actually going to write this then as pi over 3 minus pi over 4. And when we find a common denominator, we get that this is equal to pi over 12, which happens to be the equivalent of 15 degrees. So this means that we're actually going to solve the problem of finding the sine of the difference between pi over 3 and pi over 4. So remember that we're then going to do the sine of pi over 3 times the cosine of pi over 4. That symbol is going to stay the same, minus the sine of pi over 4 times the cosine of pi over 3. So we should have these memorized. So remember, pi over 3 is up here. Our point is 1/2 square root of 3 over 2, while pi over 4 is here, and that is the square root of 2 over 2 and the square root of 2 over 2 for the name of our points. A lot of times when I solve these, I actually make a chart. So I'll say the sine of pi over 3 is equal to the square root of 3 over 2, and the sine of pi over 4 is equal to the square root of 2 over 2. And then I'll do the same thing for cosine of pi over 3, which is 1/2, and the cosine of pi over 4, which is the square root of 2 over 2. So now let's start filling in and seeing exactly what we get. The sine of pi over 3, we're going to get the square root of 3 over 2 times the square root of 2 over 2 minus the sine of pi over 4, so the square root of 2 over 2 times 1/2. Remember, when we multiply fractions, we multiply the numerators together and the denominators. And the square root of 3 times the square root of 2 is actually the square root of 6 over 4 minus the square root of 2 over 4. You are welcome to leave it as this for your answer. You can also say that this is equal to the square root of 6 minus the square root of 2 over 4. Now, we cannot say, I'm just going to write a big no here, that this is the square root of 4 over 4. That's very, very wrong. This is the lowest, these two are the lowest terms of the way that you can write the correct answer. So here's the next problem we're going to work on. Suppose that alpha and beta are angles in standard position, where we know that sine of alpha is 4 over 5 and alpha lives in quadrant 2, while cosine of beta is negative 5 over 13 and beta lives in quadrant 3. And I want to know in which quadrant would the terminal side of alpha plus beta lie. So we actually should take note of a couple of things. I'm going to draw some pictures here. If I'm going to talk about alpha, And I know that alpha lives here in quadrant 2. I know a couple of things. If the sine of alpha is 4 over 5, and remember that sine is opposite over hypotenuse, I know that this is 4 and this is 5, and using my common right triangles, I know that this is going to be 3, so I now know that the cosine of alpha is negative 3 over 5. And again, it's negative because we are in quadrant 2, and cosine is negative in quadrant 2. So let's look at beta. Beta lives down here in quadrant 3. I know that the cosine of beta is negative 5 over 13, which means that I have a hypotenuse of 13. I have an adjacent side that is 5, which using the Pythagorean theorem and our common Pythagorean triples, this value is 12. Now again, remember, here I'm in quadrant 3, so the sine of beta is also going to be negative, and it will be negative 12 over 13. So you're probably thinking, okay, how do I use this to determine the answer to the question, which is in which quadrant would the terminal side of this new angle lie? So I want you to remember that if sine of alpha plus beta is less than 0, that tells us that alpha plus beta must live in quadrants 3 or quadrant 4. And if the cosine of alpha plus beta is less than 0, we know that alpha plus beta must live in quadrants 2 or quadrant 3. Now, again, if we flip this comparison sign here and we say that they're greater than, we get the remaining quadrants. So we're just going to look for overlap in where we think it could live. So let's start then with determining the value of sine of alpha plus beta. So going back to the one that we just worked on, remember, this is going to be sine alpha times cosine beta. We keep our plus sign, and then we find sine beta cosine alpha. We already have the values available to plug in, so we get 4/5 times negative 5/13 plus negative 12/13 times negative 3 over 5. So I went ahead and did the multiplication. Notice that the value of this term is less than 0 because we have a positive times a negative, and then the value of this one is positive because we're actually multiplying a negative term by a negative term. So when we take the sum of these, we're left with 16 over 65, which is definitely greater than 0, and we'll see what that means in just a moment. So now we need to find the cosine value of our angle alpha plus beta, and I've written out the formula for that here. We'll be using negative 3 over 5 times negative 5 over 13. We'll then subtract the product of 4/5 and negative 12 over 13. So we're left with positive 15 over 65 minus, and I want you to notice that this product will be negative because we are multiplying a positive number and a negative number, but then when we subtract a negative and a negative, we are left with a positive, so I'll make that here. And this is 48 over 65, which actually gives us 63 over 65, also greater than 0. So this is very important. We know that the sine of alpha plus beta is greater than 0 in quadrants 1 and quadrants 2. We know that the cosine of an angle is greater than 0 in quadrants 1 and quadrant 4, and you can see then that this is the only quadrant that they share. So it must be that these angles actually go a full rotation around when you add them and come back into quadrant 1. So we can say that alpha, let's undo that. So what we can say is that alpha plus beta, the sum of that must lie in quadrant 1.